Uh, Let me think about it. Okay. So most probably I will start a poll if everybody requires to say postpone the deadline for either project or homework assignments. I will seriously consider for that. Does it sound okay?
Yeah, sure. Thank you.
Mm-hmm. Any other question? All right, so let's start. So, so firstly, yeah, thanks for the question you just asked. That's very important because I want to say something about the final exam. So after the discussion and also the communication with the administration, I would like to give the online final exam on Canvas. So we will have this online exam exactly the same as the schedule, the original schedule that is done next Friday, I believe, is April 24th. The time should be from 10:30 to 12:30, if I'm not wrong. But please double check the website. The course website gives the time and schedule of the final exam. So the only difference this time is that we're gonna have this exam taken on Canvas. And but that's the good news is that because Canvas, those kind of online exam setting won't um, enable you to like write very complicated formulas, mathematical stuffs. That means okay, the content for this final exam will be easier than previous semesters and previous classes. Okay. Yeah, and as to some students asked about the deadline problems, like so the tradition of this class to just put out deadlines before the final exam, but if the majority of students want to postpone the deadline, say for homework or for project, we can consider for that. There should be no problem with that. Okay, so but again, even if it is possible to reschedule the deadline of the exams, not exam is not schedulable. But for homework 5 and course project, please start to do it right now because I bet no one just takes one class, right? You might have several classes in parallel. You have to deal with your projects and homeworks in other courses as well in the same time because near the end of the semester you must be very busy. So don't hurry at the last minute. If we make it, and if we consider the extension of the deadline, that's it. It's not fair to ask for an extension right before deadline. That won't make sense. Okay. Any question regarding those schedule?
Just considering that some of the material from homework 5 may be included on exam questions, I feel like that makes sense to keep that deadline, but I certainly agree that the project deadline being moved back could be extremely helpful.
Okay, thank you. I should take a note on that. But anyway, I would like to hear all of your comments, suggestion on that, and then we have to, make everybody feel comfortable. That means we should take a poll on that. Okay. All right. So let's start. Let's start the logistic regression. So this is something I want to talk about today. And also there's something you need to implement in your homework 5. So if you have finished the works on the other works in homework 5, the only remaining part will be the logistic regression. That won't be that won't be a heavy workload even if you started today. Okay, so let us first briefly review what we have discussed on last lecture. We talked about another learning framework is called Bayesian learning, right? So or probabilistic learning. So we usually have like two notions for Bayesian learning. So one notion has nothing to do with the other learning frameworks we have seen, like based on mistake-driven principle or based on computational learning theory. We just construct a loss based on some kind of principles, and then we minimize this loss, perhaps plus some regularizer to avoid overfitting, right? Typical example is the small vacuum machines. But the only difference is that we're not gonna directly predict the labels, the binary labels, 1 or -1. Instead, we assume our hypothesis is a mapping from the input to a probability, which is between 0 and 1. This probability represents, okay, how likely your predictive label is 1. Right? So we have discussed the benefit of using this kind of learning. Why? Because it can indicate a kind of confidence, right? So when I use my such kind of Bayesian learning to make a prediction, I'm not only giving you some kind of hard label, -1, a +1. Instead, I give you a probability. I give you, say, 0.9. Well, you decide in which level of confidence you believe you should decide to give a prediction 1 or -1, right? So logistic regression is a typical example of such kind of Bayesian learning, right? But there is another notion of Bayesian learning, which is a kind of different strategy or philosophy to search the hypothesis, right? So in our previous, before we talk about Bayesian learning, when we talk about learning something, we are given some kind of hypothesis space, which consists of all kinds of like possible candidates for the target function, right? We're going to search the best candidate function, which we call hypothesis. By defining some kind of loss, training loss, perhaps plus some regularizer, right? So, and Bayesian learning in general redefines how to do this search. They define this searching procedure as to find the most probable hypothesis, right? So what's the benefit of this framework? The framework is that, okay, I can first assign prior distribution over the hypothesis space. And through this prior, we can encode our prior beliefs or prior preferences about which type of hypothesis is better and which type of hypothesis is worse. And then when we incorporate to the training data, right, we just do the marriage of these prior beliefs, knowledge, and the data likelihood. Then we search for the best probability and the most probable hypothesis from their posterior distribution, right? That's the idea of the Bayesian learning to search for the best hypothesis from the data, right? So, yeah, but anyway, we don't have time to like get deep into the Bayesian learning framework, but actually this is a very big framework. It's a very big branch of machine learning. It's very in-depth. But here we just want to introduce a few very commonly, it's very widely used approach. Even in the future, you will do some work related to data science machine learning, logistic regression, and also the naive Bayes, which we're going to introduce in this Thursday, are very, very commonly used. Okay, so logistic regression, right? What I'm saying, the following ideas, linear models, those are talking about how to classify the machine learning models we have seen so far, right? Linear models, nonlinear models, and principle to conduct learning, like learning as a loss minimization. This is just what we have reviewed, right? Empirical risk minimization, regularized empirical risk minimization, right? We add some regularization term to avoid overfitting, and also learning and probability mapping, right? Map the input to some probability rather than a hard label, right? Logistic regression is such an example, right? And the Bayesian learning criterion, we're trying to find maximum A posteriori. When we assign a uniform prior, that means we don't have any prior preferences over the hypothesis space, then our map estimation turns to the maximum likelihood estimation. Okay. So today we're going to talk about logistic regression. We'll introduce what is logistic regression model, right? And then we'll talk about how to train a logistic regression. I think the major framework is exactly the same as the stochastic training for least mean square method and for SVM. The only difference is how do you calculate the gradient of the objective function for logistic regression model, right? So actually, all the tricks we have presented all the tricks before, and you have practiced them before as well. So you'll see it's very convenient to develop it by yourself. And then we'll go back and try to unify what we have derived for logistic regression into this loss minimization framework. So first, what is logistic regression? Right? So first, we'll talk about the setup. So first, logistic regression is a binary classifier. That means we want to give a prediction. The prediction is either +1 or -1, right? And the input are set of feature vectors, which we assume each feature vector is d-dimensional, right? Labels are either 1 or -1, right? And the training data are a set of pairs of input vectors and output label, right? So we assume our training set consists of m training examples, okay? So as we just mentioned, right? So although the training data are given, the labels of the training data are given as discrete values, -1 or +1, right? But instead of predicting the output, we're trying to learn from those discrete label data to predict a probability. Namely, given an input feature vector, what is the probability that its label is 1? Right? So we're going to predicting the chance or the probability that your label is 1 rather than just 1 or -1. Right? This is totally different from SVM or other perception method. Right? So you can view the learning of logistic regression is trying to expand the hypothesis space to set of functions whose output is in between 0 and 1. That means in this range of 0 and 1. Remember, when we do the linear classifier, we're actually trying to search the hypothesis who maps the input to a binary values, right? So the output region in those classifiers are just 0 or 1. It's just a discrete set, right? But in logistic regression, the output is a real value region, is a range between 0 and 1. Right? So although we're going to talk about the binary labels represented as -1 and 1, in practice, you often say, okay, the binary labels are represented by 0 and 1. Right? So in that case, we'll talk about how do you use a convenient trick to just make a simple conversion of those binary labels into -1 and 1. Okay. So actually, I haven't talked that before. So anyone can give me a hint? An idea?
Can you repeat your question?
I mean, suppose you are presented with binary data, not binary data, data with binary labels represented by 0 and 1, right? How do we convert it into a -1, 1?
We change
-2,
all.
-1.
So, yeah, go ahead. Yeah.
Oh, it's just ×2 - 1, right?
Yes, exactly. Any other approach? Supplement? Okay, I guess you two have the same idea, right? So yeah, you're right. This is a simple trick. You can just time 2 minus 1, right? We mentioned that trick before, and you'll see that in our derivation in a minute. It is very convenient. You don't need to write an if-else control flow. Don't do that. It's kind of tedious. Okay. So now, what kind of hypothesis does the logistic regression model have, right? So this is the hypothesis, namely prediction function. So the prediction function in logistic regression are parameterized by a weight vector W. This is the same as the classifier, linear classifier. Sorry. But we're gonna first do the inner product between the weight vector and the input vector, then apply the sigmoid activation function. So if you have started to do the homework, neural network problems in the homework 5, you should be very familiar with the definition of sigmoid. Right? Sigmoid is defined as 1 over 1 plus exponential to the power of negative of the input. Right? So here, the input of sigmoid is inner product between the weight vector and the feature vector. Right? So now we can say this is one hypothesis for the logistic regression. Right? So the hypothesis space of logistic regression models consists of all kinds of those functions with parameterized or indexed by different settings of W. Okay, so and again here we assume that your feature vector has been augmented with a constant feature 1. That means your weight vector is actually also includes the bus parameter. Okay, so we do not need to explicitly write down the bus parameter. We do not need to take the gradient with respect to B separately. They're done in a unified step. Okay. So the prediction function or the hypothesis function of the logistic regression is a sigmoid function composed with a linear function. Okay. So now I want to ask, what is the domain and range of the sigmoid activation function? Any idea? Come on, give me some.
The domain, I think, is from minus infinity to infinity, and the range is from 0 to 1.
Yes, excellent. Yeah, you're right? So this is a very interesting function. So I want you guys to be familiar with it. So the range, the domain of the sigmoid is just a real line from minus infinity, just as he said, right? From minus infinity to positive infinity. But very interesting property is that the output is always between 0 and 1. This is very easy to show, right? Because exponential to the power of anything is non-negative, right? So 1 plus 1 over 1 over 1 plus something non-negative will always be between 0 and 1, right? So here is the function curve. So you can see sigma actually squeeze any real value into a range between 0 and 1, right? But obviously, the larger the absolute value of the input, the more extreme the sigma function value approaching to 1 or 0, right? And the gradient of the sigmoid are largest when the input is getting closer and closer to 0, right? So this is a behavior sigmoid activation function. And also we have actually in our discussion of the neural nets, we have talked about the trick to take the gradient of the sigmoid function, right? So here we just do the brief review again. I won't write it on the whiteboard because I've done that before, right? So hopefully you guys are familiar with that, right? So if you take the derivative of your sigmoid activation function with respect to the input z, right? So just apply the chain rule, right? This is a 1 plus this exponential term to the power of -1. That means, okay, you put 1 minus 1 in front of it, and then the denominator take the power of -2, which is 1 over the denominator to the square, and then you take the gradient here, take the gradient of this exponential term, right? It is the exponential term itself. Then you have a minus sign in front of it. So you have a minus sign, you have a minus sign here. So you just they just cancel, right? So the one interesting observation is that this result can be further decomposed as the product. The first term in the product is 1 over 1 plus exponential to the power of minus c. And the second product is essentially 1 minus 1 over 1 plus exp to the power of minus c. Right? So, and we can see that according to the definition of sigmoid, so this term is sigmoid itself, right? This term is 1 minus sigmoid z, right? So that means, okay, if you take a derivative of your sigmoid, you just multiply sigmoid, multiply 1 minus sigmoid, right? So this is a very important trick. And please apply it when you implement your own neural network using sigmoid activation function, or you implement your logistic regression. Okay. So, and then according to the logistic regression model, we know that the probability, we model the probability that given your input feature vector and your model parameters W, the probability your label is 1 is sigmoid W transpose X, which can be represented in this form, right? So correspondingly, the probability that your label is -1 is 1 minus the sigmoid, and you just do this subtraction. You get exponential to the power of -1 W transpose X. That means you move this term. You replace this. You replace 1 by this term, right? And now you can divide. You can divide numerator and denominator both by this exponential term. What can you get is that you only need to change the sign. You just get rid of this minus sign. You get the probability your label is negative. Okay. So that means, okay, if you're asked to write down the probability of your logistic regression to give the prediction -1, you just remove minus sign in the definition. That's it.
Is it like probability y equals -1 or y equals 0?
No, y equals -1. So as we mentioned, right, in our setting, in our previous setting, we assume that your output is -1 or 1. So
Okay.
we're gonna keep the setting that we assume your labels are always -1 or 1, right? But yes, if you insist on using 0 and 1, yeah, you can use that as well. Doesn't matter.
Thank you.
Mm-hmm. But here, we want to, we do not want to use two distinct equations or formulas to represent the probability when y equals to 1, y equals -1. We just want to write one probability formula which encodes y, right? We do not need to write two equations, right? Two formulas, right? How can we do that? By observing the form, right? We see that, okay, the probability y equals to 1, we got this form, right? And the probability y equals -1, we got another form. So now just place y in front of this inner product. That's it. You can verify, right? If y equals to 1, yeah, we go back to this form, right? If y equals minus 1, minus 1, minus 1, they cancel. They are canceled, right? You go back to this form, right? So now go back to a question, right? Now, if I choose to represent, I choose to use 0, 1 to represent the two classes. How can I change this formula? Any question? No. Any idea? If not, I choose y. I choose to use 0 or 1 to represent your labels. How do I use one uniform probability formula to represent this probability?
We can omit the y from the denominator.
I mean, why?
We can omit the y from denominator because if it's 0, it would be exponential to power of 0 and it would be 1.
Yeah. The question is that I want to, I still want to use a uniform formula to represent this probability, right? No matter y equals to 1 or 0. And then how do we get this formula, right? How do we revise this formula to make it? Yeah, I saw some suggestion in the chart, in the chat. I'm just reading it, right? So you can replace y by 2y minus 1, right? That's it. So that relates to the question we just asked, right? So if y is either 1 minus 1 or 0, then you can simply replace y here by 2y minus 1, because then 1, 0 will be converted to 1 minus 1, right? And then all these formulas apply. Right? This is a commonly used trick. So one thing you might need to get attention is that this model, this logistic regression model, they're actually modeling the probability, the conditional probability. That is, given x, what is the chance of y taking 1 or minus 1, right? They do not care about what is the probability of the specific y, right? So this type of model in Bayesian learning is called discriminative model. So the Bayes, naive Bayes, or another type of models, if they care about the modeling of both x and y, they call it generative models. Right? So about 20 years ago, there's a whole research area talking about the connection and big goodness and badness of the discriminative models and generative models. So now suppose we have a trained logistic regression model, right? So given any test example x, I can give you a probability. And then how do you make a decision to label, right? Either how do I decide your label should be 1 or minus 1, right? So a commonly used threshold is half. That means if my logistic regression predict the probability is bigger than 0.5, then I predict 1. Otherwise, I predict minus 1. So now I want to ask what does this rule correspond to in terms of W transpose X? Or when, in other words, when this inner product will lead to a probability bigger than half, and when it will lead to the probability less than half. An idea? So it's very intuitive that, okay, I can take a look at my prediction of logistic regression, right? If the chance that you label is 1 is bigger than 0.5, okay, I predict this. I predict the label to be positive 1, right? And otherwise, I predict the label to be negative. So then in what scenarios or in what values of this inner product can lead to a bigger than half probability? Yes, right? So oh yeah, someone asked, what is the most common way of handling when the probability is 0.5? That's a very good question. Actually, there's no absolute standard. You can, if it is exactly 0.5, you can predict either to be -1 or -1. It depends. Some kind of a package, they try to use half intervals, including the positive labels, right? So if it's bigger than or equal to 0.5, okay, I predict the label to be 1. Otherwise, predict label to be -1, right? Some package they try to predict that to be -1. Totally depends on your choice. Yeah, and I saw some answers, right? Yeah, 0. That means, okay, if I use this heuristic to make hard prediction, hard labeling, only when W transpose X is bigger than or equal to 0, you have the probability bigger than or equal to half, right? Otherwise, it is less than half, right? You can show it. So that means the prediction is the same as the standard linear classifier's prediction rule. That means you just take the sign of this inner product, right? But now you can see the flexibility of the logistic regression, right? If you choose to use logistic regression, you can break out this rule by using another threshold. See, I will the accuracy to give the positive label to be very, very important. Then I can set the threshold to be 0.8. Right? Only when your probability is bigger than or bigger than or equal to 0.8, I can give the label to be 1. Otherwise, I predict them to be negative. Okay, but in this common use choice, if you choose threshold to be 0.5, then the rule has nothing different with the standard linear classifier's prediction rule. Okay. So now I have finished the introduction of logistic regression, right? The model seems really straightforward, right? Now, next, we'll talk about how to train logistic regression classifier. So again, the setting is that suppose we have already collected a set of n pairs of input and output examples, right? And we're gonna first use this maximum likelihood estimation principle for the training. Specifically, we want to find a weight vector W such that the likelihood of the training data S given this weight vector is maximized. So that's why it's called MLE, right? So, and also we know that our examples are drawn IID independently and identically distributed, right? Now let us consider how do we proceed, right? So to maximize the likelihood, we need to first write down the likelihood of the data, right? So the likelihood of data, because the IID, right? Because IID of the training examples, the likelihood of all the M training examples is equal to the product of the likelihood for each individual example, right? P of yi given xi and w, right? So we're gonna do this argmax, right? We want to find out the weight vector who maximizes this product of this likelihood, right? So obviously, if you multiply a lot of values between 0 and 1, your final value will be extremely close to 0, right? If you directly optimize this tiny product, it will be very easy to underflow, right? So to avoid numerical issues, a common use trick is just take a logarithm in front of it, right? Outside of it. And if you take a logarithm, it doesn't change the maximum because logarithm is kind of monotonic increasing function, right? It doesn't change the the behavior of your original function. So it is equivalent to maximizing logarithm of the likelihood. If you take a logarithm in front of this product, it is equivalent to take the summation, and each summation is log likelihood of each data point, right? So according to our definition of logistic regression, we know that the likelihood for a particular data point is sigma activation function of this yi w transpose xi, right? It's 1 over 1 plus this exponential term. As we mentioned, right, a unified representation of the logistic regression probability is to multiply yi in front of this inner product, right? So now just substitute this pyi given xi w. We just substitute this form for this pyi given xi and w, right? So then we get our summation to be in this form, right? So because you take a logarithm in front of it is power of -1, right? So when you move the power in front of the logarithm, it becomes a negative sign, right? So obviously we can further remove minus in front of this log by turning maximization into minimization, right? So it is equivalent to minimizing the summation of this log 1 plus exponential term. So now let's give a general view, right? So overview. So the goal is to maximize the likelihood training a discriminative probabilistic classifier, right, under the logistic regression model, right? And to do that, we take a logarithm and use a kind of mathematical rules. We end up with minimizing a summation of this term, right? And this term applied on each training example is actually defined as a special type of loss, which is called logistic loss. So in many non-Bayesian literature, non-Bayesian statistics, people call this as logistic loss. So you can see, okay, maximizing likelihood is equivalent to training a linear classifier by minimizing a special type of loss called logistic loss. Again, the connection between Bayesian method and the non-Bayesian method. So now, maximum likelihood estimation is not only what we want, right? We want to find a maximum a posterior estimation. That means we want to also add some prior information on weights, right? So how can we do that? We need to consider the prior of the weight. So here we choose a very commonly used prior, right? In most of the cases, we just use this prior. That is, we assume each element in this weight vector is drawn independently from the normal distribution with zero mean and standard deviation sigma. So if you write down the prior, so it is a product of the prior of each element, wi, right? So p of wi is a normal distribution with zero mean and standard deviation sigma, right? So this is a density of this normal distribution. So now, let us work through this procedure, right, to see how we get the map estimation. So this is the definition of the prior of the weight vector, right? So this is a likelihood, right? So if you want to maximize the posterior, we're going to maximize the product of the prior and the likelihood, right? Because the posterior is proportional to the product of the prior and likelihood. We do not need to we do not need to consider about the normalizer because normalizer is constant to W. That's something we have discussed in the last lecture, right? To maximize the posterior probability of the model given the data, right? Namely, to find the most probable model, we just need to maximize the product of the prior and the product and the likelihood of the data given the model parameters, right? So now, different from MLE estimation, right? So map estimation need us to maximize, to find the weight vector W, maximize P of W multiplying P of S given W, right? So now just substitute the form of P of S given W and P of W, right? So again, we take a logarithm, right? We take a logarithm for convenience and to avoid the numerical issue. So that means we can simplify it by maximizing logarithm of P of W plus logarithm P of S given W. Okay? Any questions so far? I assume everybody is comfortable. Okay, great. Yeah. So yeah, and then regarding logarithm P of S given W, what we have just derived is that it is a summation, right? Minus logarithm 1 plus exponential to a power of 1 minus yi W transpose xi. It's just a copy and paste, right? So if we take a logarithm of our Gaussian prior, we found that, okay, you can take a logarithm of that, right? So this sigma is kind of constant. You can just throw it out because log of the product is summation of the log of each term, right? So this term has nothing to do with W. You can just throw them out. So the remaining thing we're interested are the square of each element of W inside this EXP, right? So if you just add them together, you end up with a summation of negative Wi squares over sigma squares plus some constant. Right? So now we can throw out the constant, right? Then we do the maximization over the whole, right? The two portion of the summation. That's it, right? So obviously we can again remove the sign, right? Remove the sign, then turn the maximization into minimization, right? Maximizing a negative function is the same as minimizing the function itself. So now we end up with our objective to do the map estimation, right? So it is equivalent to solving this minimization of this log loss plus 1 over sigma squared is constant, and then W transpose W. So now I want to ask, what does this form look like? Any connection of this form to the learning objective we have seen before? Yes. Some
Primal.
can I say it again?
Primal SVM.
Prior what?
Something like primal SVM.
Yeah, exactly, right? So someone asked, the maximization doesn't apply to the prior. No, they applies, right? So remember, here is our goal, right? We want to maximize the product of the prior and the likelihood. So the maximization obviously definitely involves the prior, right? And then we take a logarithm, we just remove the sign so that we change maximization to minimization, right? So end up with this this new objective where we have a new term, right? This comes from the prior. Okay, yeah, as you guys have pointed out, right? So this form is very similar to SVM, right? So remember, SVM, we have this dot product of the weight vector itself, right? To show to reflect the margin maximization principle, right? And the first part is a loss over the training data, right? So that loss we call it training, or we call it hinge loss, is just another loss to fit to the training data, right? So now the logistic regression's objective has the same form. The only difference is the training loss, right? So here we use logistic loss rather than hinge loss. We derive this logistic loss just from our map estimation principle, right? Rather than any maximization principle. So other than any max margin principle, right? But now we can say there's a surprising similar form of the two objectives, right? Although they are derived on totally different philosophy. So now I want to ask, are you able to implement a stochastic gradient descent algorithm for this? You can just follow the SVM framework, right? How we conduct the stochastic optimization for SVM primal form, we can just apply exactly the same framework for logistic regression, right? Any questions so far? Okay, so but here, before we talk about the detailed steps of the stochastic gradient descent framework for logistic regression, I want to let you know that if your training data are not that large, another common use choice is to use LBFGS. I believe you guys should be familiar with how to call SciPy's optimization package or other like MATLAB R's package to optimize whatever function you want, like in doing your SVM homeworks. So logistic regression is we can apply that to a logistic regression in the same way. And the good thing is that logistic regression, the objective for logistic regression is convex as well. That means you can use whatever initialization, right? It will converge to the same global optimal. So now let us just follow the stochastic training of SVM primal to write down our pseudocode of the SGD training for logistic regression, right? So I'm gonna share with you the. I'm gonna share with you my pad, and I want to show you guys the pseudocode because you are required to implement this algorithm, right? Implement this training procedure. I don't want you to have any confusion on that, right? So suppose this is our training set, right? Xi, yi. Let me use another color. Suppose we have our training set, pairs of yi, right? It's from 1 to m, right? So first, in the first step, we're gonna initialize our root vector, right? So as we just mentioned, right, the objective for logistic regression is convex. That means you can initialize W with any values, say 0. That's fine, right? You can also do some random. You can also generate some random numbers to initialize, like in neural network. Totally fine. Right? The second thing is that we're gonna, like in the standard framework for SGD, right? We're gonna go through the data set multiple times, right? One pass is called one epoch, right? So we're gonna go through the data set for, say, big T epochs, right? Big T is chosen by itself, right? So inside each epoch, we'll first randomly permute. So permutate the data set S, right? To increase the randomness and to improve the robustness. And then we sequentially process each training example, right? So for each xi, yi, right, in the current order, we need to construct a stochastic objective, right? So what is a stochastic objective? We mentioned before, right? What is stochastic objective? How do we construct such a stochastic objective?
To update the weight vector for each example.
Can you say it again? Sorry, I didn't hear it very clearly.
Update the weight vector in each example.
Yeah, of course, update the weight vector for each example, right? But how do we update that? We need to write down a stochastic objective, right? What is the form of the stochastic objective?
Weight vector minus learning rate multiplied by weight vector.
Yeah, but you need to calculate some gradient, right? We call it stochastic gradient, right? But the stochastic gradient is computed from the stochastic objective, right? So we need to first work out the stochastic objective, right? So as we previously mentioned, right, to construct the stochastic objective, we need to repeat this example for m times, right? This is very important for m times. That is, we duplicate this example for m times to produce a fake data set which has the same size as the full data set, right? Then we write down the objective, the training objective on this fake data set. So that means you got your stochastic objective to be m times this logarithm of 1 plus exp minus w transpose xi yi, right? Then plus this regularization term, right? So why we just multiply this log loss by m? Because we just duplicate xi, yi for m times. So the whole fake data set consists of one unique example, right? We don't need to repeat the computation, just compute once and then multiply them for m times, right? And then we're gonna compute the gradient of this stochastic objective. This is called stochastic gradient, right? And then we use, as you just mentioned, we use this stochastic gradient to update our weight vector. Okay? So this point, 2.3, and 2.4, we're gonna update W by subtracting the stochastic gradient multiplied with some learning rate, right, or step size. Then we finished processing one example, right? And now it goes back to this step again, right? We process the next example, and then we calculate the stochastic objective and calculate the stochastic gradient and update the weight vector until we finish all the training examples in this pass, right? Then we do the next epoch, right? Until we finish all the epochs, we return W, right? So this is a framework for you to implement your logistic regression training with SGD, right? So exactly the same framework as the SGD training for SVM, right? The same thing. The only difference is that how do you construct the stochastic gradient, right? How do you compute the stochastic gradient? But the strategy is the same as SVM. You need to duplicate the example to generate fake data set. The data set must have the same size as the original data set. Then you calculate the objective on this fake data set, which is here, right? Which is here. If you, in the SVM primal, you just replace this log loss by the hinge loss, right? Then you take gradient, right? Someone has previously asked why we should do this duplication, right? I actually gave the explanation before, right? So just to refresh your mind, right? Doing this is to ensure that your stochastic gradient is unbiased. because stochastic gradient is a random variable. You need, if you want to get convergence guarantee, you need to ensure that on expectation, your stochastic gradient is the true gradient. Okay, any question regarding the algorithmic steps? Okay, everyone seems comfortable. Oh, I saw one question asking how to explain more about LBFGS, right? Okay, yeah, that's great. So LBFGS is just a quasi-optimization, quasi-Newton optimization algorithms. So basically, you can use that to optimize any function, any differentiable function. What do you need to do? Like just what you need, you have done for SVM, right? You need to fit the pair of the function value and the gradient of the function value into the LBFGS package. Then it will query different input x1, x2, and corresponding function values and gradients to decide which direction they're going to update x. But here you should see x is the parameter which we want to optimize. And here, if you call LBFGS, then f will be the learning objective of the logistic regression, right? Any question? Okay. Okay, yeah. So you should be crystal clear about this algorithm procedure, but because you need to implement your own logistic regression model by yourself. So do not hesitate if you have any question regarding the algorithm steps. Okay. Let's switch back to the slides. Okay. So now we have finished the introduction, finished the discussion about how to train logistic regression, right? So we want to give a more general view, more inclusive view about learning logistic regression, right? We want to view learning logistic regression as a principle that is called loss minimization, right? So what is loss minimization principle? We have mentioned that, we have introduced that when we talked about SVM, right? So the setup is that, the basic setup is that we assume the training examples, text examples are drawn from some fixed, but very probably unknown distribution D, right? And we assume, okay, there is some oracle, there is some ground truth classifier F, which can label examples correctly, right? And our goal is to find a hypothesis H from your hypothesis space, of course, that can best mimic F, right? So the ideal situation is that, right? The ideal situation is that we can define some function L that can penalize a bad hypothesis. Right? So, so that we won't, when we search over the hypothesis space, we can just give up those bad hypotheses. We just look at which hypothesis is best, right? So the way to fulfill their strategy is to minimize expectation of the loss function. Right? So the loss function, as we mentioned before, right, it describes the penalty that your prediction is different from your from the ground truth prediction, right? So and the golden standard to evaluate how good or bad your hypothesis is to take the expectation of this loss, right? That means, okay, we're gonna go over all possible examples in your input space, right? And say how much loss or how much penalty you have incurred on average using this particular hypothesis to make prediction, right? But of course, this is infeasible to compute. The reason is that the data distribution D is really unknown, right? So we have to compromise, right? We have to minimize the empirical loss. We can collect a bunch of training examples, right? Then we use the average of the loss on the training examples to approximate this true expectation. So you can say, if your training examples are IID, right, independent, identity distributed, so this average is essentially an empirical estimate of this expectation, right? So an average of set of IID random variables is an empirical estimate of its mean, right? So the same meaning. So that's why it's called empirical loss. So this is called expected loss. But there is also some problem here, right? The problem is that even you can minimize the empirical loss on the training set, you cannot avoid the overfitting issue, right? So if you choose the hypothesis space to be very large, that means your models are very, very complicated. It's very easy to 100% accurately fit the training data, right? Then you overfit data. If you have any noises in your training data, those noises may cause your learners to do some bad behaviors, and that was performing badly for future same examples, right? So to address overfitting, we need something that biases the learner towards simple hypotheses, right? So how do we achieve this? We have to talk about that. We can do this by using a regularizar. Right? A regularizar can penalize complex hypotheses, right? The typical example is the SVM. SVM, its regularizar is half of the inner product of the weak vector and the weak vector itself, right? So we can it can be justified that such kind of regularizar can penalize those linear classifiers who have smaller margins, right? It will favor linear classifiers who have large margins, right? And large margin indicates a simpler hypothesis space, right? So to address the overfitting, right? So we only using empirical loss will not be sufficient, right? So we in the objective function we will add one extra term, it's called regularization term, right? So that means in our learning procedure, we're gonna minimize an objective function which consists of two components. One component is the so-called regularizer, right? Who penalizes overcomplicated hypotheses. And another term is the training loss or some or empirical loss, right? Which penalize hypotheses who cannot well fit the training data. Of course, if your classifier cannot fit the training data good, enough good, that's far from sufficient, right? You should be able to fit the training data pretty good, right? But you cannot fit the training data too good, right? Even 100% accurate, that's not allowed, right? That will bring you risk to perform badly in unseen examples of the generalization performance. So this general form of the learning objective of the decomposition of learning objective is called empirical risk minimization, right? This is something we have discussed before, we have introduced before, right? So, and then quite a few methods are just instances of this empirical risk, regularized empirical risk minimization, right? So, for example, SVM, right? In SVM, the regularization term is just this term, right? Half W transpose W, and the empirical loss is based on hinge loss. And in general, if we restrict, if we remove, if we replace the hinge loss by any other loss, it is doable, right? So that means for any linear classifiers, you can use this form of the objective to learn a weak vector, right? So you have regularizer half W transpose W, and you have a whatever loss you favor. Like in logistic regression, this L is logistic loss, right? In linear regression, this loss is a square loss, right? In classification, of course, you can choose hinge loss, you can choose whatever other loss. So then that brings another question, right? So we know that loss functions should penalize mistakes, right? So we're trying to minimize the average loss over the training data. This is kind of an approximation or the estimate of the expected loss under the true data distributions, right? So among so many choices of loss functions, what is the ideal loss function for classification? An idea? What is the ideal loss function? Or what kind of loss function do you think is ideal? Hinge loss or square loss? Yeah, that's good. That's somebody said, okay, it should be convex. Yeah, that's good. That's a good point, because convex can give you a lot of guarantees, right? If it's not convex, actually, it's very hard to say something about that. Any other suggestion? Okay, but from the most naive point of view, right? If you want to define a loss function, the ideal situation would be if you make correct prediction, you won't be penalized. Right? If you make incorrect prediction, you will be penalized, right? In other words, if you make correct prediction, your loss should be zero, right? If you make incorrect prediction, you should be under some penalty. So such an ideal loss is called 0-1 loss. Right? So 0-1 loss is something theorists favor much. You can derive a lot of things out of that. So you'll see a lot of things. You'll see a lot of theories and conclusions based on something that you choose the 0-1 loss, and how other types of losses are related to 0-1 loss in computational learning theory. Right? So here's 0-1 loss, right? So 0-1 loss penalize classification mistakes between true label y and prediction y prime. Right? So that means if your prediction y, if your ground truth y is not equal to prediction y prime, then your loss is 1. Otherwise, your loss is 0. Right? So if you choose linear classifiers, this is the prediction function, right? This is the prediction score, and you make prediction by taking the sum of your prediction score, right? So if you make a mistake, that means the ground truth label multiplying with your prediction score is less than or equal to 0. Under such kind of case, your 0-1 loss is 1. Otherwise, it's 0. Right? But although the 0-1 loss is ideal and has many good theoretical properties, if you directly minimize 0-1 loss, it's very hard because it is intractable. The most obvious reason is that it is very hard to take the gradient. So it's a step function, right? So it's very hard to take the gradient, even the subgradient. If you take subgradient, you find the subgradient doesn't make sense. The subgradient is 0 for both cases. So people in practice will never use 0-1 loss to train the data, right? So we need some surrogate of 0-1 loss. In other words, the logistic loss, the hinge loss, the square loss, and all kinds of other loss can be viewed as some kind of surrogate to this 0-1 loss. Okay. So we can start with perception loss, hinge loss, exponential loss, logistic loss. Perception loss, remember we have discussed how we view training of perception as using stochastic subgradient descent approach to minimize some loss, right? So this is a form of loss. If you feel strange about this form, just go back to look at our previous slides, right? Hinge loss is from SVM, and exponential loss is from the eta boost and logistic loss, right? So actually, we can create a loss function zoom, right? So if you just have one-dimensional input, right, and here is the 0-1 loss, right? So the x-axis represents your prediction score, namely W transpose X, right? So W transpose X is here, and this figure shows how the loss function values vary along with different prediction scores in x-axis, right? So the ideal loss is 0-1 loss. So you can say, okay, if your prediction score multiplying, sorry, the input should be the prediction score multiplying with the y, right? So if this input is less than zero, meaning that your prediction is wrong, then you incur a loss 1, right? Otherwise, if it is positive or non-negative, you're making correct predictions, so the loss is always 0, right? So, but for other type of losses, namely surrogates, right? The behaviors vary much, right? So for those losses, generally we won't have like only penalizing wrong predictions. So you can see many those kind of losses, even your input is positive, meaning that you make correct prediction, you have to be under some kind of penalties, right? So this is 0-1, so this is hinge loss, right? So you can see hinge loss, this blue line here is essentially a upper bound of the 0-1 loss, right? And perceptron loss is kind of intersect with hinge loss at the origin, right? And also at some point on the left-hand side, right? And eta boosting loss, right? Eta boosting is kind of the hinge loss is kind of tangent line to the eta boosting loss, right? And eta boosting loss is also the upper bound of the 0-1 loss. And also here's our logistic loss. So actually, in practice, you can define whatever loss function you want, as long as it is reasonable in marrying how your model fits the training data, right? So that means you can add whatever animals in your loss function zoo. Any questions so far? Okay. Yeah. So now I have finished the introduction of logistic regression. So it is based on the Bayesian learning principle. We want to learn a function which predicts a probability rather than a hard label, 0-1, right? So based on this scope, we can use the Bayesian principle. We write down the joint probability, the prior of the weight vector, and the likelihood of the data given the weight vector, so that we multiply them together, we can maximize this product to find the map estimation of weight vector, right? But when we do this map estimation, we find that it can also be explained as an instance of the regularized empirical loss minimization model, right? So you can say this is a kind of another example of the strong connection between different learning principles, Bayesian learning and non-Bayesian learning, right? So to summarize, logistic regression is a classifier that predicts the probability that the label is 1 for a particular input, right? Particular probability rather than the label itself. It is called discriminative classifier because we are modeling a conditional probability P of y given x. Okay? We're now trying to model x, namely the input features. If we jointly model the input features and also the output label, it's called generative model. And the logistic regression is discriminant classifier that minimizes the logistic loss over the training set. This is another view, right? Empirical risk minimization, right? Okay, so we have finished early today. So any question so far? Everybody's comfortable? Okay, I will use the remaining 3 minutes to answer any kind of questions. So anyone who wants to create the Zoom room, please feel free to create. I'm gonna shut the room in 3 minutes. Oh, someone asked if we have addressed the final exam or number of lectures left. The final exam is scheduled on next Friday, April 24th. The time should be in the morning from 10:30 to 12:30, I guess. But please double check on the course website, and also we will make an announcement later in Canvas. So we're gonna do an online Canvas exam. So the difficulty will be, I mean, it will be much easier than the paper problems. But you need to join that. You cannot skip that, right? So, and the second thing is how many lectures left. After today, there will be 2 lectures. So one lecture will be on Thursday, and next lecture will be on next Tuesday. And on next Tuesday, I will give a brief review of this course, and then we'll talk about the practical, some suggestions about how to practically using machine learning. Does this sound good? Any other question? Okay, great. So anyone, if you want to talk about the homework or final exam or course project further with me, please join the office hour starting from 2, and still the same link to the Zoom room. Okay, see you on Thursday.